All right, so coming in here, since it's still early in the semester and you're still just getting to know my procedures and all that, typically most days when you come in here, you'll see a slide like this is going to have the outcomes. Well, since we have announcements after announcements, you'll see a slide that looks like this, and I'll have some sort of opening question. That's usually just for something you'd write down in your notebook and just kind of be thinking about what today is going to be about. I didn't put one today because we really haven't covered that much today other than scientific method and all of that. So go ahead and make like, not necessarily a T-chart, but just I need you to write down these two things: exact numbers and inexact numbers. Or I'm going to put over here measured numbers. All right. So I'm going to start with the measured numbers. What would be some examples of measurements that we would take in this class? Or what would be some examples of measurements that you've taken in science classes in the past? Okay, milliliters. What kind of what class of measurement is milliliters concerned with? Like distance, volume. All right, so milliliters is volume. So we're going to measure things in volume. So that'll be typically in milliliters, liters. If you're buying a soft drink, it might be in ounces. All right, but that's liquid volume. We also have dry volume that we can do length times width times height, and we'll get things like centimeters cubed, meters cubed, inches cubed, things like that. So when we're talking about exact numbers or measured numbers, one of the things that I want us to know is that we can only we can only be as precise as the tools that we're using to measure the item. So in this classroom, I have two different scales that we'll use from time to time. All the scales that we use are digital scales. So I have this digital scale, and it only measures to 1 decimal place. That's only as precise as it can be. So if I put something on here, it'll say like 5.3 grams. Whereas this scale, with the little box over it and all of that, it's a much more precise scale. It goes out to 3 decimal places. So this one measures out to the thousandths. This one only measures to the tenths. So I can be much more precise with my measurements on this one. And I can know it to a greater degree of certainty. Whereas this one, I'm kind of, if it says 5.3 grams, it could be 5.349, something like that. Whereas on that one, if it's 5.3 grams, I know it. If I say 5.300 or 5.300, I know that it is exactly 5.300. So, if you're trying to be really, really specific with your measurements, you want a more precise tool. If you're not being as precise with it, you can not as specific with it. You can use a tool with less precision. So if you're talking about one of my brothers is a machinist. When they're measuring things and when they're cutting things out, they go to like a micrometer sometimes, and they have these really, really specific tools that measure the inside diameter, outside diameter, and all of that. And I mean, they get really, really tight tolerances. So that's going to be like for machine parts and all of that, and, in these big industrial equipment that have to work well all the time. Whereas you go buy a little cheap remote control car or something like that from Walmart or wherever, and you start looking at the tolerances of that, when you get two exact ones from the same store, from the same company, and you start really measuring things, and you're going to find out that those parts, the tolerance isn't as tight. It's an injection molded plastic and all of that, and it's not going to always be exact. So the more specific you want to be. So measured numbers are always going to have uncertainty. Meaning there's going to be a part of that number that we don't know for sure. All right. Now, for exact numbers, for an exact number that I can give in here is that there are 19 human beings in this room. All right. There's 18 students, one teacher. All right. So an exact number is something that we know and I mean, one way to look at it is we know it to an infinite number of decimal places, no matter how I slice it in here. When we say there are 19 people in this room, that's 19 to an infinite number of decimal places. So if we use that 19 in a calculation, we're not going to use that number to determine the number of sig figs. We would have to use something compared to a measured number that we know how many places we have. All right. So exact numbers are going to be things like counting numbers, so example, number of students in a class. All right. So things like number of students in a class, how many eggs in a carton, things that you can physically count and all of that. Measured numbers is going to be things that you use some sort of tool to measure. So like time is considered to be a measured number. Distance, length, volume. Anything that you have to use some sort of device to determine that number is going to be measured. That's going to be inexact. We only know it to a certain degree of certainty, whereas exact numbers is infinite certainty. The other thing that goes as an exact number is conversion factors. So one conversion factor that we're going to use in this class pretty early on is like the comparison between inches and centimeters. All right. We know that 1 inch is exactly 2.54 centimeters. All right. That conversion factor is not going to change the number of sig figs in our answer when we go from inches to centimeters. All right. Another conversion factor that we'll use is like maybe meters to millimeters. So base unit to milli. We know that for every 1 meter, there's 1,000 millimeters. So from base to milli is always a difference of 1,000. And so that conversion factor is not going to affect our answer. We have to look at what we were reported with in the beginning. All right. So questions on that? All right. All right. So when we're looking at those measured numbers, and I've already made this statement, so you don't have to really write it again. But everything that is measured will always have a degree of uncertainty, and you have to look at what tool we're using. So there's always going to be an estimated number in that measurement that we don't fully know what it is. So typically in a measured number, the number that we're uncertain of or unsure of is the last reported digit. So if I take a measurement on my scale back there and I say that it weighs 5.312 grams, the number that's going to be uncertain is that 2. In reality, that could be a 3, it could be a 1, it could be a 0. It's just I'm having the computer, the programming of that scale is just giving me a number on its best I guess the best algorithm it can use to give me a number to show me a number. But it doesn't necessarily mean that we are totally sure of that number. It could be a little bit more, it could be a little bit less, because this 2 could be representing, if we were just looking at that 2, it could be representing something like a 1.87. It could be representing a 1.5, and it's just rounding it. So it's kind of like a rounded number at the end. All right. So if you're like measuring the global temperature, all right, if you watch, different things talking about climate change and all of that, they usually report an average global temperature. All right. So if you look at historical documents, you can find out that the average global temperatures have risen by 0.6 degrees Celsius over the last century, over the last 100 years. All right. It doesn't mean that it's went exactly 0.6. What that really tells us is this number could be something like, could be 0.55 degrees, or it could be 0.64. Both of these numbers would round to 0.6. So if we're only reporting it to a precision of 1 decimal place, then I could have a range from 0.55 to 0.64 and still be 0.6. All right. So by reporting the temperature increase of 0.6, the scientists mean that that 0.6 is a plus or minus 0.1 degrees Celsius, that it can go up or down. So if you watch like during election times and all of that, and they report the polls, and they'll always say to a degree of uncertainty or a degree of error of plus or minus 3 or something like that, that's the same thing. There's always this range that we're not real sure about that number, but we're fairly confident in the number. All right. So again, depending on the data you use, you could end up with a number as high as 0.7 and a number as low as 0.5. If you took another data set and then over time you average them out, it's going to come out closer and closer and closer to 0.6. All right. But the thing that I want to make sure is that we know we can't go up a whole place. So like I can't report it as a 1.0 on that one. All right. And again, don't feel like you have to write every one of these down. because all I'm doing is clarifying some things. All right, does anybody need more time on this or want more off of this or whatever? I will probably post these later. All right, so I have 3 different rulers. Take a minute, look at these rulers that we're measuring with. They're all measuring maybe different things and all of that. But of these rulers, which one would you say is the most precise ruler? All right, second one, why? All right, it measures to the 10th. And then what can we guess about when it's in between 2 tenths? Yeah, we can measure to the hundredths place. I mean, we can estimate to the hundredths place on this one. On this one, what's the best estimate we can do on this? To the tenths. All right. So I can say it. I know for certain it's 6, and then I know it's beyond 6, so I can estimate a tenths place. We're pretty good with our eyes that we can divide that in half, and then we can divide it in half again. So I could probably say something like 6.2 or 6.2, 6.1, 6.3 in there, kind of guessing at where the halfway mark is. All right, on this one, same thing. If that represents about a halfway mark, I know it's about at least that on there. So if I'm reporting a number off of here, I can say it's 0.47 maybe, 0.46, somewhere, and get away with that number. All right. And then looking down here, if we had to estimate a number or give an uncertain number, what place is the estimated number going to be on this one? The ones place. So the best guess that we can give on that one is possibly like 60, 64, 65, somewhere around there. We can't know it to there. So the best number I can give here is 65 centimeters or 64 centimeters. 19 of us in this classroom, we might come up with probably about 4 different answers on that, just judging from our perspective. All right, same thing here. I might call this one 0.46. All right, somewhere around there. This one, I might call it 6.2. Somebody else might say 6.3. I know it's not 6.5 because it's not halfway. But I know it's less than 6.5. All right, but I don't know exactly how much less it is. All right, so again, don't feel like you have to copy everything off of this one. I'm just going to kind of go through it again. So on that first ruler, the device is marked to the ones place. So our uncertain digit is the tenths. So this is our uncertainty. I'm still going to write it down. So it's kind of like an estimated digit, but I'm still going to write it down because I'm fairly confident in that number and I want to use it, but I can't. I have to make sure that I am also being safe with the number, that I'm not over reporting it or things like that. All right, and same thing for that second ruler. You see, they gave a different number than I read it as. That second ruler is marked to the tenths place, so that means we can estimate the 100ths place. All right, and then same thing with the last one. This one is measured to the tens place, so that means we can estimate the ones place. Now, they said it's a little over half. That's perspective. All right. Here's the thing. In this class, most of the time where this is going to come into play is when we're using graduated cylinders. So there's going to be different graduated cylinders that we use in this class. All right. One of them might mark 1, 2, 3, 4, 5, 6, 6, 7, and then this one and I know they're not. All right, so we have these two different measurement, two different graduated cylinders here. I'm going to say that the first one, the one to the left side, is maybe a little bit bigger, taller. They're not the same size, but I struggle with drawing those kind of things. So if we had a water level on both of these and we were trying to get a measurement off of these, one of the things I want to talk about when you're reading a graduated cylinder, you always read it, the liquid's going to have a curve on it, and you always read it from the bottom of the curve. All right, now how precise can I be on this one? What's the precision that I can read this one with? Or let me ask the question like this. What number do I know for certain first? I know the ones place. I know it's greater than 4, right? And it's less than 5. So I can put that 4 down with certainty. All right. What can I estimate here on this one? I can estimate the 10th place, right? So we have to make a guess of where we figure it falls between 4 and 5. Now there's no real scale to mine, so you can come up with a lot of things. So let's just say that it is, based off of what I'm seeing, that I'll say it's like 4.3 milliliters. All right. Now on this one, we know 4 for certain. We know it's less than 5 and greater than 4. I also know, I kind of know this 10th number for certain to a pretty good degree. I know it's less than 0.5, and it's right pretty close to that 0.5, so I can almost say 4.4 there. And now I can actually estimate in the hundredths place on this one because it kind of measures to the 0.5. All right, so I can go ahead and put in there, let's just say that it's 4.45, something like that. All right, so we can go all the way out to the hundredths place on this one. We can only go to the tenths place on this one. All right. So that's one of the things that when we report these numbers. So as we progress in this unit, this only has 2 significant numbers or 2 significant figures, whereas this one will have 3 sig figs. When I'm using this in a calculation, my answers, if I'm doing numbers using this graduated cylinder, all of my answers can have 3 sig figs. If I'm using this one, my answers can only have 2 sig figs. All right. Or really all of my answers can have 2 decimal places, and this one can only have 1 decimal place when it comes to it. All right. Questions? Let's move on. All right. So here are some rules. I do need you to get all of these down. 4 significant figures. Any non-zero number all non-zero numbers are considered to be significant. And so what I mean by that What I mean by that is when we see a number written on the page, if I see a number written on the page like 1,340, anything that's not a zero in this case is considered to be significant. So this number, as it's reported right here with no decimal points, no other markings or anything like that, the only numbers that I'm going to consider significant is the 1, 3, and the 4. So there's 3 sig figs in that number. So what does that mean that zero must represent? How many of y'all have ever been to like a large sporting event and listened to the announcers when they talk about how many people are in the stands? Do they ever say that there are 54,332 people in the stands, or how would they report that number? They'll say there's 55,000 people at this event. All right. So where do those zeros come from, or what are those zeros whenever they report a number like that? Rounded. All right. So this zero, reason why I can't call it significant is because it's most likely rounded. All right. So this number might actually be something like 1,335 or 38, and I just rounded it and got that number. All right. So that's the first rule. All non-zero digits are significant. The second rule, an interior zero, a zero that's sandwiched between two other numbers, is going to be considered significant. So if I have 1, 0, 3, and I'm just kind of use the same numbers. If I have 1, 0, 3, 4, 0, so 10,340, how many significant figures do I have in this one, or what numbers are going to be significant in this one? The first 4. All right, so there's 4 sig figs in that. Again, that last 0 is rounded. All right, so if I had another number, like 106, how many sig figs in that one? 3. All of them matter in this one. So that 0 that's caught in between becomes significant because that means we've actually counted it, or we actually know it's there. It can't be rounded because it's in the middle of a number. All right. Rule 3. A trailing 0 to the right of a non-zero number that fall after a decimal point are significant. All right. So if I have a number like 13.000, how many sig figs does that number have? 5. Every one of these zeros is important. If I write a number like that and I put that decimal point there, and even if I say it zeros beyond it, I'm telling you that I know that number is exactly 13.000. All right. So all of those are going to be important. All right. How about that number, 140.0? How many sig figs would be on that one based off of that rule? 4. Everything becomes significant. So this one hits the rule that it's sandwiched. This one hits this rule that it's a trailing 0 behind a decimal point. All right. So now I'm going to take my original number right here, 1340, where it was 3 sig figs based off of this. But if I write this, come on. If I write it 1340 decimal point, how many sig figs does it have now? 4. Because I put that decimal point there, it says that I know that number is a 0. All right, so all 4 of them count in that one. All right, is it making sense? All right, trailing zeros. Trailing zeros that fall before the decimal point are significant. So I just talked about that one. So coming into this one again, so if I have two different numbers, if I have 1,000 and I have 1,000 with a decimal point, which one has more sig figs? Second one. This one, all four numbers count. And in this one, the only number that we can know for sure is significant is the 1, because there's no way to know if that's a rounded 1,000 or if that's a thing like that. So that decimal point, the presence of a decimal point, makes all the difference in the world of how many numbers we report. Now, so most of the time, students are with me until I get here, and then the next few are where confusion comes sometimes because we want to overthink the answer. So the only time you're ever going to have leading zeros is in a decimal number. And in this class, we are going to take measurements that end up being really, really small. So we might have 0.00 something. All right. So in this one, rule number 5 says leading zeros, zeros to the left of the first non-zero number, are not considered significant. So if I have a number like 0.00450, and I'm being intentional about that number, how many sig figs would be in that number? Or where do we start counting the sig figs in this number? All right, so in this one, we don't start counting until the first non-zero number. All right, why do you think I'm not counting those? What are we going to call these types of numbers? All placeholders. I think I heard it. All these are placeholders to let me know that this starts in the thousands place. All right. More than likely, this was a number that we measured in a smaller unit and we converted it to a larger unit. So we might have measured it in millimeters and we converted it to meters or something like that. All right. So if you have a number that has a decimal point and it's zeros at the beginning of it, you don't start counting until the first non-zero number. All right, so I'm going to underline a word on this one. Implied. So if I write a number down like 120, most of us in our mind is thinking, okay, so we counted out 120 items. And so we imply a decimal point there. We just automatically say, okay, it's there. But we don't write it in the prompt, and the prompt on your test didn't write a decimal there or anything like that. And we're trying to figure out, when we do our answer, how many sig figs are we going to have to report in our answer and all of that. We can't assume that decimal point is really there. What we have to assume is that this number may be possibly a rounded number, just like before. So when we look at this, the only numbers that we know for sure is that 1 and 2. That 0 is considered to be ambiguous, meaning we don't actually know the value of that. We don't know if it's a significant figure or not. So when we write numbers, and if I'm trying to say there's 3 sig figs there, I need to be specific by putting a decimal point there or writing it in scientific notation, which we'll get to probably on Tuesday of next week. So just kind of keep that in mind. And I want to make sure. Yeah. All right. So you kind of get the idea of this. All right. It's not hard. It's just that we have to be careful about we have to be careful about paying attention to how we write the numbers and being intentional about how many numbers we want to say that we know for sure. All right. All right. We already talked about that. All right. So let's look at a few numbers. Go ahead on your notebook. I want you to write down these numbers, and then somewhere next to them, you can even number them or whatever if you want to do. I want you to try to determine how many significant figures are in each of these numbers. All right, so what do you think? The first number, 0.0035. How many sig figs do we think is in that one based off of the rules we just went over?
35.
Just the 3 and the 5 are significant. So that means that we would call this 2 sig figs. All right. So there's 2 significant figures in this one. All right. How many significant figures in 1.080?
3.
All right. So going by the rules, that 0 is sandwiched, so it counts. So we know at least 3. And then that's a trailing 0 after a decimal. So everything counts in that one. All right. So that one is going to have 4 sig figs in it. All right. How many sig figs in 2,371? 4. Everything counts. All non-zero numbers, nothing to indicate anything being rounded or anything like that. Now, the next number is written in scientific notation. So, when we look at this one, let me just see what we think first. How many significant figures do you think are in this number? Just 2. The only numbers that count right here is those 2. So it's 2 significant figures. So I'm going to talk about what that times 10 to the 5 gives us. Remember at the beginning of class, I talked about that we still have to maintain the value of the number. So that 5 is giving me the value of it. So what that times 10 to the 5th is telling me is that I have 290,000. Is that I'm actually looking at 290,000. But the only numbers I knew for sure were the 2 and the 9. And so it's just a different way of reporting a number with value when you don't want to write down all of those zeros and you don't want to be ambiguous. We want to be specific about showing that it's only 2 sig figs. All right. And like I said, I'll get more into writing those later, how we convert one number to the other and all of that. All right. So now, if I told us that we had a dozen eggs or 12 eggs, how many sig figs is in that? All right, think about what kind of number is a dozen. Is it an exact or measured? Exact. So in that case, when it's an exact number, sig figs are unlimited, meaning it will not affect your calculation answer. They won't change the answer as far as the number of sig figs. All right. So essentially, we know that it's 12.00000000 infinity 0, exactly 12 to that point. Sorry. And just go ahead and check. So for 100.00 is 5 sig figs. And then this last one, 100,000 with no decimal point, how many sig figs? One for sure. I would call this 1 sig fig. Textbook and sometimes on a test, they might, if you're given a choice of ambiguous for it, I would go with the. All right, we don't know for sure where the rounding begins on this one. I could know for a fact that it's 100, that the 100 works, but the last 3 zeros are rounded. I don't know. And so for this one, we can only know for sure of that one. All right. Questions, comments, concerns? So far, this is easy stuff, right? Yeah. All right. Now I'm going to start making it hard. All right. So we have some rules for when we're doing calculations. Addition and subtraction calculations. In addition or subtraction, the result carries the same number of decimal places as the quantity that carries the fewest decimal places. So remember my graduated cylinders that we were using earlier, that I drew earlier. So I had the one, I had the one that measured, graduated cylinder that measured to the tenths. All right. And let's just say that I had a volume of water in there, that I start off with 3.52 milliliters of water in it. All right. And I am trying to find the volume of a rock. All right. I drop that rock into the graduated cylinder. When I drop that rock in there, what's going to happen to the water level? It's going to rise a little bit. So it's going to go, and I'm just going to pretend it went from there, and it goes to there. All right. And so it goes up, and the new reading is now 4.41 milliliters. All right. When we do, what this is saying is if I did a calculation and I'm trying to find out the volume of that rock, I'm going to go 4.41 minus 3.52. And now we have to do some subtraction there, and I don't want to tax my brain because it's first period. So I'm going to go ahead and cheat. All right. So when we do this number, we get 0.89. Now, I will say that if I had these numbers specifically, most of you on the test would probably get it right because there's no change to it and all that. What I'm going to tell you, though, is no matter, this number can get infinitely large, and it doesn't affect our answer. But we can only ever have 2 decimal places. All right? So we have to report it in 2 decimal places. Yes?
So if you have like a whole number minus a number with 1 decimal point, your answer
should be a whole number. All right. Now, just be careful carrying that over into a math class. Math class may want it a different way. In here, if you have a whole number with no decimal place and you have something that's 1.44 and you subtract it, your answer is only going to be to the ones place. All right. And I'll show some examples.
Wait, so what does that even mean?
I'm going to try to show it with an example first, and it may clarify it. So, yeah, so this rule applies only to when we're adding and subtracting numbers in this class. All right, so let's look at it in this way. So let's look at an addition problem. All right, so I took three measurements. One measurement, I was using a ruler that I can only go to the hundredths place. One measurement, two of the measurements, I used a ruler that I can go to the thousandths place. All right, so I need to add these three measurements together. So I have 5.74, I have 0.823, and I have 2.651. All right, notice how I put it in column math so you can see it a little bit better. Odds are when it's on a test, it's going to be written out linear. All right, but my least precise measurement is that one. All right, it only measures to 2 decimal places. So when I add these numbers up, if I ultimately add it, I'm going to get a number of, if I put it in the calculator or whatever, I'm going to get 9.214. But when I write the answer down on the test, what answer do I need to write? 9.21. All right, that's all that rule tells us, is that we look at the least precise measurement in our list for addition and subtraction, and our answer has to be reported to that many decimal places. All right, so if we're subtracting 2 items, one of them has 3 decimal places, one of them has 4 decimal places, no matter what our whole number is, our decimal can only go to the smaller amount of decimal places, so like 3 in that case. All right, so try this one on your own, see what answer you get. Now, before I even answer this, or before we show anything, my final answer, what kind of format would my final answer have? What's to the tens place? All right, so I'm going to have something like x point x, right? I don't need to know the numbers at this point. I'm just kind of showing generic. All right, so that's the max I can write. So when we do the calculation, we get 0.835. Now, that 3 in this is important because if it was 0.855, that would change my answer a little bit. But right now, it's just 0.835, so 3 is less than a 5, so that means we can just drop it off. So what's my final answer going to be? 0.8. All right, does it make sense? Okay. Now, I'm going to make this statement in it. The rules for addition subtraction are to be kept separate from the rules of multiplication and division. All right, so kind of think about it when you're doing addition and subtraction. Pay attention to how many decimal places something is. When we shift over to multiplication and division, we are going to start looking at total number of sig figs. Notice I didn't say anything about how many sig figs any of these had. All right, we don't start worrying about how many sig figs until we're multiplying or dividing. All right, so multiplication and division rule. The result of a multiplication or division carries the same number of significant figures as the factor with the fewest significant figures. So one of the first types of calculations that we're going to do with sig figs is density problems. All right. So density equals mass over volume. So if I have an object and I tell you that the volume so I have a volume of 3.42 milliliters and a mass of 1.352 grams. Don't necessarily want to solve it right now, but how many sig figs can I write my answer in? 3. So based off of this rule, my answer can only have as many sig figs as the one with the fewest. This is the one with the fewest. It has 3 sig figs, so my answer is only going to have 3 sig figs. All right. So now, doing it, I don't really care about the answer on it, but the setup, 1.352 over 3.42, you'd set it up like that, just divide. All right. I don't, like I said, I'm not worried about the answer, but our answer can only be 3 sig figs. So, and I will show this because, so we end up getting from the calculator something like 0.395321637. Depending on your calculator, the numbers at the end might be a little bit different, but so we get all of that. But what would my final answer look like on this one? All right. So there's my 3 sig figs. I do need to look at this number because if this number is 5 or greater, I'm going to round this number up. All right. So my answer because I'm dividing grams by milliliters. So 0.395 grams per milliliter. So that object would float. All right. So let's look at some examples. All right, first example I have is we have 5.02 times 89.665 times 0.10. When we do that calculation, I get 45.0118. And when I go to write the answer, how many sig figs can my answer have based off of this problem? 2. So what is my answer going to be? Should be 45. All right, so my answer can only be in 2 sig figs, and it can be 45. All right, looking at the second one, division and multiplication work by the same rules. So 5.892 divided by 6.10 gives us a decimal of 0.96590. How many sig figs can my answer be? 3. All right, so I can only have 3 sig figs. So 3 sig figs, what will my answer be? 0.966. All right, why did we change the 5 to a 6? Yeah. So since if this is the 3 sig figs I'm looking for, this 9 needs to, I need to account for that. So I'm going to call it a 6. I'm going to round up because it's greater than 5. That part doesn't change. Now, one thing to be very careful of, if that would be like if that would be 99999, don't start back here and round, because that's going to make this number significantly larger than it should be. So don't multiple round, just round from the number that's right behind it. Yes? Density equals mass over volume. It's M is mass, V is volume. Is that what you were asking, or were you asking about the answer?
No, I was asking about that.
Okay. All right. So any questions about this rule, the two rules, addition, subtraction, multiplication, division? Any questions about how we determine the number of sig figs? All right. We get out of here at 8:50, right? Okay. So 7 minutes. All right. I'm gonna pass something out. This is just like supplemental to the notes. It's not something that you it's not something that I'm gonna pick up for homework. All right. So this is just kind of supporting some of the stuff that we did with measurement. 3, 4, 5. 2, 3, 4, 2, 3, 4, 5. 2, 3, 4, 5, 6, 7, 8. All right. So like I said, just so that we are clear, I am not going to pick this up. I'm not going to grade it. Use it how you use it, just as reinforcement for what we talked about today or things like that.